Good morning, everyone. My name is Aryan Parekh, and I'm an MSc Computer Science student at Western University, specializing in the domain of AI, and currently working on Advanced Driver Assistance System or ADAS. Today, I'm thrilled to share the results of our comparative analysis of YOLOv8 and RTDETR models, which are focused on their capabilities in real-time object detection for ADAS. This research was conducted under the guidance of Professor Michael Barr, and I'm eager to discuss how these models perform in diverse real world scenarios. Thank you all for joining this session, and I look forward to an engaging discussion following the presentation. Yep. So, the agenda for today's presentation uh, is following. We'll explore the role of object detection in advanced driving assistance system and emphasize its importance for vehicle safety and automation. We will also outline our research objectives comparing YOLOv8 and RTDETR models for these systems. Literature review will provide the context, which will be followed by the description of the experimental setup, including the datasets that we have used, the tools that we used, and the evaluation metrics. The results for this research will highlight the detection accuracy and processing speeds with an analysis of each model's strengths and weaknesses. And finally, we'll summarize the key findings and invite questions, if any. Introduction. Advanced driving assistance systems rely on sophisticated object detection technology to navigate complex environments and identifying pedestrians, vehicles, and road signs to enhance safety and improve traffic efficiency. This discussion focuses on two key object detection models, YOLOv8 and RTDETR. YOLOv8 and RTD, yeah, yeah. So YOLOv8 is a CNN-based model which is renowned for its speed and accuracy in real-time applications. And in contrast, RTDETR is a transformer-based model which offers advanced scene understanding by handling complex dependencies. So we'll evaluate these models to determine their effectiveness in the domain of advanced drivers assistance system or ADAS. Objective. Our research focuses on two key metrics for ADAS technologies, which is detection performance and inference time. Detection performance ensures accurate object identification for safety, while inference time measures the speed of real time decision making in dynamic traffic environments. We aim to evaluate RTDTR, which is a promising transformer based model, and check if it can match or surpass YOLOv8 in ADA specific scenarios. While RTDTR has shown superior results on general datasets like COCO, we seek to determine its suitability for driving applications, which is a crucial step in autonomous driving and assisted driving systems. Okay, coming to the literature survey, I've divided that into three sections. First would be the YOLO models for object detection. Second is transformer based models. And third is the datasets that we explored. So, talking about YOLO models, the YOLO family has transformed real time object detection, treating it as a single regression problem. YOLO V1, which was introduced in 2015, introduced single pass predictions but struggled with small and overlapping objects. YOLO V2 improved the batch normalization, anchor boxes, and multi scale training, while YOLO V3 added residual blocks and upsampling for better accuracy. There are other evolutions, but due to the time constraints of the presentation, I'm not gonna go a lot into that. But we have covered all of that in our paper. Finally, I'll be talking about YOLO V8, uh, which, with its efficient backbone and anchor-free design, excels in detecting pedestrians, vehicles, and traffic signs in real time, which makes it ideal for resource-constrained environments. Now, coming to the transformer-based models, they have also advanced in object detection. DTR reframed detection as a set prediction problem, eliminating anchor boxes but facing slow convergence. So this DETRs actually marked the shift of transformer-based models into object detection. Otherwise, before they were actually used in NLP for natural language processing. Yeah. Deformable DETR improved efficiency with deformable attention mechanisms. And finally, RTDTR, which is real-time detection transformers, it optimized self-attention for real-time applications, balancing accuracy and computational overhead, making it suitable for ADAS. Now the key datasets. So key datasets include first BDD100K, which is an extensive annotation for diverse conditions. Next dataset that we explored was the road lab dataset, uh, which had traffic object detection in Canadian environments. Cityscape, which had semantic segmentation and detection in urban settings. New scenes dataset, which was a 360-degree sensor data for 3D detection. And finally, Kitty dataset, which was a benchmark for 2D and 3D object detection. And finally, Waymo Open dataset, which focuses on urban object detection. These advancements in dataset enhance ADAs but highlight the trade-off between performance and inference time. Okay, great. Coming to the experimental setup. So I've divided the experimental setup into four parts, which is dataset selection and preparation, model architecture, training and testing setup, and evaluation metrics. So coming to the dataset selection, we selected two datasets, which was BDD100K, which is known for its extensive annotations and diverse driving conditions, making it suitable for ADA's benchmarks, and Road Lab, which was tailored to Canadian driving scenarios. It provides high resolution traffic object data, and it was developed by Western University. For pre-processing, all images from these datasets were resized, normalized, and subjected to data augmentation techniques such as random cropping and horizontal flipping. This ensures that the models are trained on consistent and robust data. And moving on to the architecture of the models we tested, so YOLOv8 is, and so those the models are YOLOv8 and RTDTR, which we have already discussed. But I'll be diving a bit into the architectures of these. YOLOv8 is an evolution of the YOLO series featuring an optimized CSP Darknet 53 backbone that improves gradients and gradient flow and reduces complexity. It introduces an anchor-free detection head, which eliminates predefined anchor boxes to streamline the detection process and reduce computational overload. Enhanced feature pyramid and path aggregation networks allow for efficient multi-scale object detection in YOLO. Next, coming on to RTDTR models, they represent a shift towards transformer-based model architectures, which is ideal for real-time applications. It uses multi-head self-attention to capture global image context and includes deformable attention modules that focus more precisely on relevant image paths. Optimization in attention mechanism and processing strategies ensure it meets the speed requirements for real-time ADAs. I'd love to dive more into the architecture of these two, but due to the time constraints, we can't cover all the technical details today. But I encourage those interested to explore the detailed discussion in the published paper on these models. Coming to the computational setup for training and testing, we utilize Compute Canada's Graham and CADA servers equipped with NVIDIA V100 GPUs. The Graham server was dedicated to BDD 100K dataset, while CADA handled the Road Lab dataset and overall testing. For training, both models were initially pre-trained on Coco dataset to establish a baseline in general object detection capabilities. Specifically, YOLOv8 and RTDTR were trained for 160 and 200 epochs on BDD 100K and Road Lab respectively, with batch sizes of 16 for YOLOv8 and batch sizes of 8 for RTDTR to accommodate for the memory constraints. We maintained a fixed learning rate of 0.01 across all the experiments to ensure consistency in training conditions. Finally, let's talk about the evaluation metrics. We measured average precision, mean average precision to understand uh, precision at various recall levels and across different intersection over union thresholds. We looked at precision and recall to evaluate the proportion of true positives detected and the model's ability to identify the relevant instances. The F1 score was also crucial for balancing the precision and recall, which is particularly valuable in scenarios of imbalanced class distributions. We'll talk more about that in the later result discussion. And lastly, frames per second or FPS was a key metric because it reflected each model's ability to process frames quickly, which is a critical factor for ADAS performance. Yeah, so this is the summary of the datasets used. Uh, we took the entire BDD 100K as one dataset, but we broke down road lab into four different categories, which is traffic objects. So traffic objects would have pedestrians, vehicles, traffic sign, and traffic signals. And traffic vehicles, signals, and signs were broken down into their respective own categories. The reason for doing that was because this ensured a robust testing ground for comprehensive model evaluation. Okay, coming to the results now. So I've divided the results into three parts. Uh, so the first one would be detection performance over epochs. This evaluates how quickly each model learns and converges to a higher map, which is crucial for efficient real-time deployment. The next thing we focused on was map versus latency trade-off. This was to assess the balance between accuracy and speed, which is essential for ensuring timely responses in ADAs. And finally, we have F1 score, which measures how well models handle class imbalances, which is vital for detecting both common and critical objects in diverse driving scenarios. Right. So coming to the first part of the art results, which is development of detection performance over epochs. I'm not sure if I can zoom in over here. No, I don't think I can. But yeah, detection. So our study compared YOLOv8 and RTDTR models across various data sets. So first one you can see is the results from BDD 100K. If you see, you'll observe that YOLOv8 models, especially YOLOv8X, achieved stable map values for 0.35 after 160 epochs, and it outperformed RTDTR, which peaked below 0.32, indicating faster and more effective learning. And then, if you check the roadlab data sets, particularly first, if we look at the object dataset, which is the first one, YOLOv8X achieved 0.37 map, which outperformed RTDTR's 0.23 map. And even over the building of epochs, at every stage, YOLOv8 has been a fast learner over RTDTRs. Similarly, for vehicle data set, if you observe, YOLOv8X and YOLOv8L excel the maps with around 0.45, while RTDTRs remain only around 0.23. Uh, Sign dataset. YOLOv8 models maintained around zero point 0.3 map, while RTDTR showed instability in the sign dataset. And even for the signal ones, YOLOv8 reached around zero point 0.4, but RTDTRs made it around zero point 0.3. So these findings highlight YOLOv8's superior and consistent performance across diverse detection tasks. Coming to the second part of the results is the map versus latency trade-off. So let's observe that for the BDD 100K dataset. We can see that YOLOv8X demonstrates superior efficiency, which achieves 36.4% map at only 4.5 milliseconds latency. So we are basically looking for a model with higher map value and lower latency value because we wanted to evaluate fast, right? Better at a faster pace. So that is exactly what YOLOv8 does. It achieves a map of 36.4 at 4.5 milliseconds, but RTDTR just achieves 32.2 map at 9.5 milliseconds. So clearly YOLO is better in this one. Now, similarly for all the road lab datasets, YOLO for the road lab object dataset, YOLOv8x achieves 37.1% map with 5.9 ms latency, whereas RTDTRX achieves 23.3% map with 7.2 milliseconds latency. For the vehicle one, YOLOv8x and L achieve like significantly outshine RTDTRX again. For the road lab sign dataset, YOLOv8 achieves 33% at 5.9 milliseconds, whereas RTDTRX achieves 25% map at 6.9 milliseconds. And for the signal dataset, YOLOv8 excels with a 40.1 map at 6 millisecond latency, but RTDTRs only achieve 17.5% map at 6.9 milliseconds. So in all the datasets, it's clear that at least in the comparison of map versus latency trade-off, YOLOv8 is still better than RTDTR. Next, in our analysis of, I have just made a plot over here for of latency on x-axis and the map values on y-axis. So basically, we are looking for higher map values, so that would be on top of the graph, and lower latency values, so that would be towards the left of the graph. So basically, models that lie on the upper left part of the graph are going to be better than the ones below them, right? And the ones on the bottom right are going to be worse. So for all the plots, you can observe that the YOLO family lies on the upper left part, but RTDTRs tend to lie on the downward right part, indicating that YOLO gives better performance with lower latency than RTDTR. Finally, coming to the third part of our result, which is F1 score analysis. Now, one more thing, what is the need for F1 score analysis? So the reason for that is in ADAs, the class imbalances and driving datasets pose challenges as vehicles are more common than pedestrians or traffic signs. Just have a look at the graphs over here, and you would observe that the instances of a car in all the datasets that we have is much more than the instances of pedestrians or traffic signs or anything. So this can lead to models to favor frequent objects over rarer ones. So the F1 score addresses this by combining the precision and recall into a balanced metric, ensuring models perform well across both common and rare object classes. This balance is crucial for reliable ADA's performance in diverse real-world scenarios. So that is why the F1 score is important. And we need a model with a higher F1 score. So that indicates that uh, the model performs better even for classes with lower instances. And if you observe the table over here, for even for the BDD 100K, you'll observe that YOLOv8x has a F1 score of 0.617, but RTDTRs have only 0.592. So yeah, in almost all the cases, that's the result. That F1 score you can observe on the tables here, and in the research paper published that uh, YOLO performs better than RTDTRs even in case of F1 score analysis. So yeah, those were the findings of the paper. To conclude, this paper analyzed YOLOv8 and RTDTR models for real-time ADAS object detection across 5 datasets, and YOLOv8 consistently outperformed RTDTR in detection accuracy and inference time, with YOLOv8 models showing YOLOv8x specifically showing faster convergence and higher map values and adapting well across diverse datasets like BDD 100 and RoadLab. YOLOv8 also demonstrates superior balance between map and latency and achieves high accuracy with faster processing, making it ideal for real-time ADAS tasks. Also, its higher F1 score highlights its effectiveness in handling class imbalances, which is crucial for detecting critical objects like traffic signs and pedestrians. And coming to the future research and development, so future research could explore YOLO V10, which is a model that recently came out for potential improvements, and it could also we could also explore probably like hybrid architectures combining YOLO's detection efficiency with context uh, transformer-based model contextual awareness for specialized driving scenarios. And yeah, that's it. So thank you for your attention, everyone. And this concludes the presentation for the paper. Have a great day.